Hi, everybody. So welcome to our third independent weather investigation. So what I wanted to do for this part of it is model how the collision and coalescence process works. So the collision and coalescence process is one of the two major precipitation processes in our atmosphere. It is that in warm clouds, and then in cold clouds, it is what is called the Bergeron process. So I have a different video that models the Bergeron process. So we'll get to that one in a few minutes. But for right now, let me model how the collision and coalescence process works. In any cloud, particularly warm clouds, there's going to be an assortment of water droplets. And these water droplets, for a number of reasons, have different sizes to them. Because of a different cloud condensation nucleus, a little bit bigger, or because maybe it's had a little bit more time in the cloud, so it's been able to grow a little bit more. Either way, what you end up having is these assortment of cloud droplet sizes. Some are bigger than others. And the way that these work is the larger droplets actually fall faster than the smaller droplets. However, it would be physically misleading for me to tell you that it's because they're heavier. Actually, they're not. Instead, what is happening, well, they are heavier, or the larger droplets are heavier, but that's not why they fall fast. So to demonstrate why they fall faster than smaller droplets, what I'm actually going to do, and I strongly recommend, if not ask you to do this at home as well, because you're going to get a much better visual of it if you do it at home versus if you just watch me do it. What I recommend that you do is get two objects. A heavy object like this set of keys that I have right here, nice and heavy, and then a light object. So right here I have a washcloth. It's definitely lighter than my keys. Another thing you can do is you can grab a piece of recycled 8.5 by 11 paper. This was from another class some time ago. And take it and ball it up. Balling it up is really important, and I'll explain why in a moment. But to demonstrate how the collision coalescence process works, I have these two objects now. I have a set of keys, and I have a balled up piece of paper. From the same height, so got to make sure that they're just about the same height, drop them and see which one hits the ground first. I'm not going to tell you which one hit my desk first because I want you to do it. Okay, so now with that out of the way, let me explain why smaller droplets fall slower than large droplets. Smaller droplets have a lot of surface area relative to their mass. Here's what that means. So think of this ball of rolled up paper right here. Everything on the exterior is the ball's surface mass. However, there's plenty of mass on the inside of this rolled up ball of paper. All of the mass isn't concentrated on its surface area. Now, if I were to unfurl this piece of paper, like so, 1 second, please. If I were to unfurl this piece of paper and try my best to reduce the wrinkles, obviously it's a wrinkled sheet of paper. It's going to do what it does. If you notice now, all of its mass is surface area. Now think about what happens. Let me turn off my fan so I can make sure that I show this very, very easily. Watch what happens when I drop this paper now compared to when it was balled up. Do you notice that as it's falling, it kind of wafts down, it kind of drifts down? The reason why this happens is falling. It's not falling into empty space. No, it's actually falling into occupied air. And so there's wind resistance as it's falling. There's drag. as it's falling, that causes the rate of descent to slow. That causes the rate of descent to slow. However, when it was all bunched up, like so, it fell really fast. So smaller droplets, believe it or not, are more, whoops, I tore the paper. That's okay. Are more like this than they are like a balled up piece of paper. As a result, you have larger droplets, like my keys, falling in a cloud filled with smaller droplets, like these wafting sheets of paper. The collision and coalescence process works just like this. Boom. In that case, what you noticed was the slower moving sheet of paper was eventually caught up with, or eventually caught up by, my falling keys. And as that happened, the two collided, that's the collision, and the two bonded, they fell in unison. That's the coalescence. Strongly recommend do this at home. And in fact, some of the questions I'm going to ask you hinge on you being able to do this at home. So once again, all you need to model this: set of keys, sheet of paper, or any other light object would work as well. But you also want to have something with a large surface area like this sheet of paper. So the last thing I'll talk about really quick is what determines how big a droplet gets, how big a raindrop gets. I don't know if you've ever felt rain before that felt like these gigantic, huge, wet drops falling really fast. On other times, you might feel like the rain is very spritzy, very sprinkly, very light. Well, the big difference between those two types of droplets is how much time the drop spends in the cloud. If we have a raindrop that spends a long period of time in a cloud, then that raindrop is going to have more opportunities to collide and coalesce. That means that the raindrop is going to have an opportunity to get bigger and bigger and bigger. On the other hand, if the raindrop doesn't have a lot of time to spend in the cloud, it's going to very quickly fall out of the cloud and reach the ground. During that time, it's not in an environment that allows it to grow. Actually, quite contrary, it's in an environment that forces it to shrink. So some of the things that actually determine how long a droplet spends inside a cloud: one, how thick the cloud is. This is one of the reasons why when you see really thin clouds overhead, no rain falling from them, because they're just too thin. Any water droplets that form in them evaporate quickly after falling out because they're just too small. So you need a thick cloud. And typically in very, very heavy rain, you get something called an updraft. Basically, if you recall all of that adiabatic cooling and rising air stuff, well, a big blob of rapidly rising air is what is referred to as an updraft. And in the case of updraft, these droplets, as they're falling, they begin to feel a little bit of resistance pushing them up, keeping them in the cloud for longer. So that's another thing that can influence how big a water droplet can get. If something forces it to stay in the cloud longer, it's going to become bigger and bigger. So you need a thick cloud, and you also need some kind of updraft. And if you get both of those things, you can get really big raindrops.